9. Existential out. We now have 3 rules. We have both an elimination out and an introduction in Rule 4, and we have an introduction Rule 4. At the moment, however, we do not have an elimination Rule 4. That is the topic of the current section. Consider the following derivation problem. 1 xfxhxpr 2 xfxpr 3 xhx. One possible English translation of this argument form goes as follows. 1. Every freshman is happy. 2. At least one person is a freshman. 3. Therefore, at least one person is happy. This is indeed a valid argument. But how do we complete the corresponding derivation? The problem is the second premise, which is an existential formula. At present, we do not have a rule specifically designed to decompose existential formulas. How should such a rule look? Well, the second premise is xfx, which says that something, at least one thing, is f. However, it is not very specific. It doesn't say which particular thing is f. We know that at least one item in the following infinite list is true, but we don't know which one it is. 1 flaw 2 fb 3 fc 4 fd etc. Equivalently, we know that the following infinite disjunction is true. D flaw fb fc fd. Once again, we pretend that we have sufficiently many names to cover every single thing in the universe. The second premise xfx says that at least one thing is f, something is f, but it provides no further information as to which thing in particular is f. Is it A? Is it B? We don't know given only the information conveyed by xfx. So, what happens if we simply assume that A is f? Adding this assumption yields the following substitute problem. 1 xfx hxpr 2 xfxpr 3 xhxdd 4 flaw? I right? Because the status of this line is not obvious at the moment. Let us proceed anyway. Well, now the problem is much easier. The following is the completed derivation. A 1 xfx hxpr 2 xfxpr 3 xhxdd 4 flaw? 5 faha 1, 06 hectares 4, 5, 07 xhx6, I. In other words, if we assume that the something that is f is in fact a, then we can complete the derivation. The problem is that we don't actually know that A is f, but only that something is f. Well, then maybe the something that is f is in fact B. So let us instead assume that B is f. Then we have the following derivation. B1 xfx hxpr 2 xfxpr 3 xhxdd 4 fb. 5 fbhb1, 06 hb4, 5, 07 xhx6, I. Or perhaps the something that is f is actually C, so let us assume that C is f, in which case we have the following derivation. C1 xfx hxpr 2 xfxpr 3 xhxdd 4 fc. 5 fchc1, 06 hc4, 5, 07 xhx6, I. A definite pattern of reasoning begins to appear. We can keep going on and on. It seems that whatever it is that is actually an f and we know that something is, we can show that something is h. For any particular name, we can construct a derivation using that name. All the resulting derivations would look virtually the same, the only difference being the particular letter introduced at line 4. The generality of the above derivation is reminiscent of universal derivation. Recall that a universal derivation substitutes a single model derivation for infinitely many derivations, all of which look virtually the same. The above pattern looks very similar. The first derivation serves as a model of all the rest. Indeed, we can recast the above derivations in the form of UD by inserting an extra show line as follows. Remember that one is entitled to write down any show line at any point in a derivation. U1 xfx hxpr 2 xfxpr 3 xhxdd 4 xfx xhxud 5 fa xhxcd 6 fa 7 xhxdd 8 fa 1, 09 hectare 6, 8, 010 xhx9, I11 xhx2, 4. The above derivation is clear until the very last line, since we don't have a rule that deals with lines 2 and 4. In English, the reasoning goes as follows. 2 At least one thing is f. 4 If anything is f, then at least one thing is h. 10 Therefore at least one thing is h. Without further ado, let us look at the existential elimination rule. Existential out. If a line of the form VFV is available, then one can assume any substitution instance fn of fv, so long as n is a name that is new to the derivation. The annotation cites the line number, plus O. The following is the cartoon version. OVFVN must be new. That is, it cannot occur in fn any previous line, including the line VFV. Note on annotation: when applying O, the annotation appeals to the line number of the existential formula VFV and the rule O. In other words, even though O is an assumption rule, and not a true inference rule, We annotate derivations as if it were a true inference rule. See below. Before worrying about the proviso so long as n is, let us go back now and do our earlier example, now using the rule O. The crucial line is marked by example 1 xfx hxpr2 xfx pr3 xhxdd4 fa2, 05 faha 1, 06 hectares 4, 5, 07 xhx6, in line 4, we apply O to line 2, instantiating x to A. Note that A is a new name. The following are two more examples of O. Example 2 xfx gxpr2 xfx and hxpr3 xgx and hxdd4 fa and ha2, 05 fa 4, and 06 hectares 4, and 07 fa ga 1, 08 ga 5, 7, 09 ga and ha 6, 8, and I10 xgx and hx9, example 3 xfx gxpr2 xgx hxpr3 xfx and hxid4 xfx and hxs5 dd6 fa and ha 4, 07 fa 6, and 08 hectare 6, and 09 fa ga 1, 010 ga 7, 9, 011 ga ha 2, 012 hectares 10, 11, 013 8, 12. Examples 2 and 3 illustrate an important strategic principle in constructing derivations in predicate logic. In example 3, when we get to line 6, we have many rules we can apply, including O and O. Which should we apply first? The following are two rules of thumb for dealing with this problem. Remember, a rule of thumb is just that. It does not work 100% of the time. Rule of thumb 1: don't apply O unless until you have a name in the derivation to which to apply it. Rule of thumb 2: if you have a choice between applying O and applying O, apply O first. The second rule is, in some sense, an application of the first rule. If one has no name to apply O to, then one way to produce a name is to apply O. Thus, one first applies O, thus producing a name, and then applies O. What happens if you violate the above rules of thumb? Well, nothing very bad. You just end up with extraneous lines in the derivation. Consider the following derivation, which contains a violation of rules 1 and 2. Example 2 revisited 1 xfx gxpr2 xfx and hxpr3 xgx and hxdd fa ga 1, 04 fb and hb2, ob is new. A isn't. 5 fb4, and 06 hb4, and 07 fbgb1, 08 GB 5, 7, 09 GB and hb6, 8, and I10 xgx and hx9, the line marked is completely useless. It just gets in the way, as can be seen immediately in line 4. This derivation is not incorrect. It would receive full credit on an exam supposing it was assigned. Rather, it is somewhat disfigured. In examples 1-3, there are no names in the derivation except those introduced by O. At the point we apply O, there aren't any names in the derivation, so any name will do. Thus, the requirement that the name be new is easy to satisfy. However, in other problems, additional names are involved, and the requirement is not trivially satisfied. Nonetheless, the requirement that the name be new is important, because it blocks erroneous derivations and in particular, erroneous derivations of invalid arguments. Consider the following. Invalid argument xfx xgx/xfx and gx at least one thing is f, at least one thing is g/at least one thing is both f and g. There are many counterexamples to this argument. Consider two of them. Counterexamples: at least one number is even, at least one number is odd / at least one number is both even and odd, at least one person is female, at least one person is male / at least one person is both male and female. Argument A is clearly invalid. However, consider the following erroneous derivation. Example 4 erroneous derivation 1 xfx pr2 xgx pr3 xfx and gxdd4 fa 1, 05 ga 2, wrong. 6 fa and ga 4, 5, and I7 xfx and gx6, the reason line 5 is wrong concerns the use of the name a, which is definitely not new, since it appears in line 4. To be a proper application of O, the name must be new, so we would have to instantiate gx to gb or gc, anything but ga. When we correct line 5, the derivation looks like the following. 1 xfx pr2 xgx pr3 xfx and gxdd4 fa 1, 05 GB 2, right. 6. But we can't finish now, the derivation cannot be completed, but that is good, because the argument in question is, after all, invalid. The previous examples do not involve multiply quantified formulas, so it is probably a good idea to consider some of those. Example 5 1 xfxy high pr2 xfxy high cd3 xfx s4y high dd5 fa3, 06 flaw y high 1, 07 y high 5, 6. As noted in the previous chapter, the premise may be read if anything is F, then something is H, whereas the conclusion may be read if something is F, then something is H. Under very special circumstances, if any, is equivalent to if some. This is one of the circumstances. These two are equivalent. We have shown that the latter follows from the former. To balance things, we now show the converse as well. Example 6:1 xfxy high pr2 xfxy high ud3 flaw y high cd4 flaw as 5 y high dd6 xfx4 i7 y high 1, 6. Before turning to examples involving relational quantification, we do one more example involving multiple quantification. Example 7:1 xfx xgx pr2 xfxy ud3 flaw y cd4 flaw as 5 y id6 y 7 dd8 GB 6, 09 xfx4 I10 xgx1, 9, 011 GB 10, 012 8, 11. As in many previous sections, we conclude this section with some examples that involve relational quantification. Example 8:1 xyk xyr xypr2 xyk xypr3 xyr xydd4 yk2, 05 cab4, 06 yk ray 1, 07 cab rab 6, 08 rab 5, 7, 09 y ray 8, I10 xyr xy9, example 9:1 xyr xypr2 xyr xyrx xpr3 xrx xy rix pr4 xyr xyud5 y ray ud6 rab dd7 yrb y1, 08 rbc7, 09 yrb yrbb2, 10 rbc rbb9, 011 rbb8, 9, 012 rbb yrib3, 013 yrib11, 12, 014 rab13,